We're working on probability. We're going to finish off doing some more expected value questions. I'm going to look at examples of what they mean by a fair game. And that's a very generic version of the expected value. There's different versions depending on the circumstances of the question. And then after that, we are going to be doing a large section on sample spaces and probabilities. But we'll tackle them when they come. Okay, so expected value is a term that we use to try and put a number on what you would expect to get if you were doing a gambling game. And essentially, would you win money? Would you lose money? Would it be really a lot of money you'd lose, or would it be a very tight game? There are some games where they're called a fair game. A fair game is when the expected value is a zero, when it's zero. You're not going to get them in any casinos because that means the casino doesn't make any money, and you don't make any money because everybody, wins $5, but then they lose $5, right? And so we're looking at that term. Is a particular game fair? What that means is, does it have an expected value of, say, zero? So I'm going to zoom over here and show you a homework question like that. And here we go. Fingers crossed. Right, you should be looking at question 5 right now with the spinner one. Right. Now, in this particular situation, you pay $5 to play the game, right? So your stake is going to be $5. And you do the spinner, and if it points at the top guy, it's $8. And if it points at the bottom guy, you get $2. So you're getting money back, but remember, it's cost you $5 to pay. So you don't want the spinner to be pointing at the $2, right? You'd prefer the spinner to land on the $8 because that way you made some money, right? You made $3. So let me jump back to the whiteboard and we'll look at how we would tackle that question. So the picture looks something like that. And $8 if it points up there, and you get $2 back if it does that. And your stake or your bet is $5. And we are being asked, is this a fair game? And what that means is the expected value zero? If it is, the answer is yes, it's a fair game. If it's any other number, it's no, it's not. So, well, I just thought of something. Can I use EV from now on instead of having to write expected value all over the place? You okay with that, EVs? So it's going to be the amount you win, which is $8, times the probability that it lands on the $8 mark, added to $2 times the probability that it lands on the $2 mark, and take away your bet, which is $5. So 8 times, and this spinner is a very simple one. Would you agree that the probability it lands on the $8 is a half, and in the $2 it's also a half? So it's 8 times a half plus $2 times a half, take away 5. So that's $4, that's $1, take away 5, and the answer is 0. So yes, it's a fair game. Now, if we kept the question exactly the same, except to change one thing, suppose it cost you $6 to play the game. These two would stay the same, but wouldn't you subtract 6? So can you imagine what the answer would look like at the end? It would be 4 add 1, which is 5, take away 6. That would be -1, and that would not be a fair game. In fact, in that particular game, wouldn't the casino be winning money off you? I can't imagine that being a casino game, but the gambling organization would be winning money from you. And so negative means you lose. In the long term, you lose. Positive expected value means in the long term you will win. And a zero expected value means that you're not going to win or lose. You could play the game theoretically forever. Now, the second version of this is a spinner that looks something like this. Over here, it's $2. This piece here is $5. And this big chunk in here is $8. And in this game, your stake is $5. Okay, so we're going to find what the expected value is this time. So it's going to be $2 times the probability that lands on the $2. It's going to be $5 times the probability that the spinner lands on the $5 mark. It's going to be $8 times the probability of being 8, and now you're taking away 5. Right, I don't know how well I've drawn this shape. I've tried to make it accurate. Would you agree that the probability in here is a half? Great. Half the circle, half the probability. So this is a half. This is, if I put in a pretend little dot, do you see this is split into equal pieces? So what's the probability that the spinner lands on the number 5? What's the probability it lands in this little region here?
1/6.
Correct. And would you agree then 2/6 for the other one, which is a third, but I'm just calling it 2/6. So I'd probably keep them as, well, you can do anything you like, but I would probably keep them in fractions right now. That gets you 1, that gets you 5/6, and that guy gets you 16/6, take away 5. And then at some point, you're going to go to your calculator. So I'm going to do it now. So it's going to be 1 plus 5/6 plus 16/6, and then take away 5. And the answer I get is negative 0.5, which in the money world becomes negative 50 cents. And in this situation, aren't you going to lose money? And the answer that you do in your homework is to choose the not fair option. All you get is two options. You pick not fair or you pick fair. But that's how you would discover it. You can use this number. If I played this game, if I was a compulsive gambler and I played this game, say 100 times, then I would expect 100 times this funny guy. I would expect to be $50 down at the end. Right, I'd play 100 games, right? And I'd expect to be $50 down at the end. Now, if you think about it, if you play it 100 times, aren't you gambling $500? And if you lose 50, right, because that's what the negative is telling me, I'm going to lose $50. That means essentially you got, I guess, a lot of fun, right? You played a game, I'm assuming that it was interesting to you, and it cost you $50 to play. So as long as you think of gambling as a kind of fun thing to do, you're probably okay. If you think you can gamble and make a living out of it on normal gambling machines, you're going to go broke. And that's not a good idea. Is there anything about these last two questions that we're having issues with? Right. I'm going to show you, because it's easier to show you than me to trying to draw it, the last two questions. I'm not going to do them because I want you to get practice at your homework as well. But I do want you to have a look at the spinners. this spinner, your stake is $10, and this is kind of the payout. And I can do one of these really long calculations and come up with the exact expected value, and there's nothing wrong in you doing that. But if you are going to do that, you'll need to know the probabilities. So let's do the probabilities. The chances that it lands on a 2 is a half. Agreed? What's the chances it lands on the $4 area? It's a fraction. What's the chances that, yeah. And what's it for the 8 and the 14? Because they're both the same size. I'm assuming they're both the same. Yeah, they are. The $4 is a quarter. The $2 is a half. And what are the two baby guys that are left? One something. One what?
Oh, 1/8.
1/8. Right. In different ways of looking at it, but here goes. Would you agree that the two of them together is the last a quarter? And half of them in each, half of a quarter is an eighth. Would that be one way of looking at it, how you come up with the eighth? I'm not doing that calculation, but I know the answer, and it's not because it's in front of me. I can make an intelligent guess. Do you think you're going to win money, lose money, or do you think that's a fair game? I agree. Tara's doing the thumbs down. What about the numbers and the spinners that's kind of telling you this is not going to be a game you're going to walk away with money most of the time?
The bigger parts of the spinner are the smaller increments. So you're got a higher probability of hitting something that's $8 or $6 less than what you paid.
Less, yeah. Yeah. So can you imagine in that question, it would be totally valid because the way the question is just to say it's not fair. I mean, I wish they'd given you 3 choices. It's fair, you would lose money playing this game, or you would win money playing this game. Because I think in that case, it gives you a little bit more variation, but that's what you would do. Now, here is the ultimate version of ugly. In this case, you know, can you imagine you just throw a coin onto a board, and if it lands, you know, it randomly bounces about, and if it lands on the place, that's what you get. In this particular one, there is a dart being thrown, and if you hit the board where it says $1, that's what you get. If you hit the $10, you get $10, and it says how much should you be willing to pay. And you think, well, how can I tell how much am I willing to pay? Because I'm not a gambler and I don't know how much people pay to play games. What they're really hidden here is they want to know what the stake money would have to be to make this a fair game. So what you're going to do is you're going to calculate all of these guys. So I'll give you an example. It's going to be $1 times a half. It's going to be $6 times a quarter. It's going to be $10 times, what's that guy worth? That's a half, $1. The $6 is a quarter, right? It's a quarter of the whole shape. What's a tenth? A $10, I should say. What fraction is that?
1/8.
Yeah. And what's the $8 and the $4 going to be?
1/16.
What? 1/16. So do you see how it's you know, you had to think quite hard about what fraction each shape is. Now, I don't know, looking at that, what that total's going to be, but let's just pretend it ends up being $18, just a number off the top of my head. Then you should be using as your answer, I am willing to pay $18, right? That's the most I'll bet on that game, right? That would be what I'd be willing to play, right? If it's $4.20, then you will type in $4.20, right? So you're only going to calculate all the prices that you get, what you'll get when you win, times the probability, and add them all up. And my gut feeling, and it's not very good to have a gut feeling, It's about 450. That's my gut feeling, somewhere probably about there. Just curious, has anybody done that question? Has anybody done this?
I tried to
guy
work on it, but I couldn't figure it out.
Okay, I tell you what, it's curious. I want to find out now, right? And since it's not one of those variable questions, I think I can get away with it. So although you can't see what I'm doing right now, once I've written it down, actually, what am I saying? I can make the picture go away because I can still see it on my second screen. And you're just going to have to trust me that I'm doing the right numbers. Okay, so there was a $1, and that's going to happen half the time. There was a $6, and that's going to happen a quarter of the time. There was a $10 that happened 1/8 of the time. There was an $8 1/16 of the time, and a $4 1/16 of the time. And I'm just going to go for glory and hope I don't hit the wrong button. 1 times a half.
I just did it too. I just got it done.
Keep that number, and if I get the
So-
same one, then I'll feel happy, right? So it's 1 times a half, add 6 times a quarter, add 10 times an eighth, add 8 times 1/16, add 4 times 1/16, and the answer I have is a very nice round 4. Did you get that? And what was my
Yep.
gut feeling? About 450, I think I said. I'm kind of pleased with myself. Wasn't that a pretty close guess?
So I have one question
Yeah.
because I was doing it a little bit different on the fractions, only because for me, when I'm like writing, if it's only like 2 or 3 numbers, I don't have a problem with doing like the multiple fractions and splitting them up. But on this one, because there's so much going on, I use the same base number. I found the smallest one, it was 16. So then I did it so that I could double check my math. That's not going to make it screwy later on, will it? I just
No,
want to make
it's
sure
not.
that it will. Because then I could see at the end that I had 8, 4, 1, 1, and 2. So I had 16 of 16. So I knew I counted every square, so I didn't have to worry. And then when I was putting it in the calculator, it made it a little bit easier because then I was doing the top number by the same bottom number. It didn't feel as confusing. I was just worried that if I do it that way, it would mess it up somewhere. So as long as it doesn't mess me up, I'm happy.
It is cool. I want to show the rest of them what you're saying. What you did here, if I picked you up right, I think I did, is that you changed all these fractions so that they all were 16ths. They all shared the common denominator. So a half was 8/16, right? And a quarter was 4/16. And then she did a quick check and she said, "Look, okay, 8 add 4, add 2, add 1, adds up to 16. And 16/16 is good. So I know I didn't screw up there. And if you keep them as a common denominator, you could, if you wanted to, then couldn't you just go 1 times 8, 6 times 4, 10 times 2, 8 times 1, and 4 times 1, and add them all up over 16, right? I'm assuming that the answer is 64, and you got 4.
This is a very good job.
Do you like that way? I like it. It's a good way of doing it. Came out nice. I guess I'm just lazy. I just hit buttons on calculators after a while because it's me. It doesn't mean the way I did it is the best way to do it. It's just the best way for me. And in a lot of ways, isn't that what you should be doing anyway? I like doing it this way rather than that way. The bottom line is, are you doing it correctly? Are you getting the right answer? And if the answer is yes, then do it. Are we good with spinners and expected values? Can we call that one done? Or is there any other questions from that section?
Will you
you'd
go
like me
over
to go
one? Will you go over one more from yesterday? I'm pretty sure that I have it all the way down of how to like write it out so I can calculate it, but like the ones where it gives you 5 quarters and 5 dimes and 5 nickels, I think that I had it right.
Oh yeah, I need help with that one too, by the way.
But I wouldn't mind.
Okay,
having
let's do
another
that.
one.
I can do that, not a problem. I'm trying to find it. I think it was question 3. Is that correct?
Yes.
Yeah,
Okay.
it was like 2 and 3 were those type style questions. I just wanted to make sure.
Not a problem. Let's do that. There's somebody in chat might be asking something. No, just tell me she's here. Okay. Let's look at that question. Suppose you have 10 quarters, 10 dimes, 20 nickels, and 10 pennies in your pocket, and you reach in and you choose a coin at random and you give it to your child. What is the expectation? That's what I call the expected value. And your answer is going to be 2 decimal places, because it's going to be, 0.12, right? $0.12. So in this question, I'm just going to write down the details. There's 10 quarters, 10 dimes, 20 nickels, and 10 pennies. Now, the way WebAssign does things is that if you ever see anything in red, it means it's a randomized number. So you may look at the same question and it won't be exactly the same numbers. So it's really the process that you should be learning, not just this one question. So let's put this guy together
I'm just scared because I'm
and
reading about it.
see what's going on. Okay, so I'm just going to pause for a second. Got someone who needs to come into class. You're going to have to hit the space button if you want to say things. Right. Just to get the background sound out of the way. Right, so there are 10, 20, 30, 40, 50. There is a total of 50 coins in that person's pocket. And the reason I'm doing that is because I'm now going to find all these probabilities. If I stick my hand in my pocket, the chances I pick a quarter is going to be 10 out of 50, which if you simplify it down is 0.5. If it's going to be dimes, it's the exact same. It's 10 out of 50, which is a fifth. Nickels, 20 out of 50, 2/5. And pennies, 10 out of 50, 1/5. Are we happy about how I found the probabilities of the one coin that I'm going to take out my pocket and give it to the child? Right. Now, the expected value formula is basically the value of that, right, how much it's worth, times its probability. So it's going to be the quarters, which I'm going to call 0.25, times the probability of you getting a quarter. So that's the quarters times the probability of getting a quarter, plus a dime times the probability that you get a dime. And a dime is 10 cents times fifth. And a nickel is 5 cents times a fifth. And last but not least, pennies times the probability that you picked a penny. And a penny is only 1 cent, and the chance that you actually got it is a fifth. And now that I've noticed, I should be consistent and making sure that everything is the right way. And then I just multiply this whole mess together, because that's the way my brain works. So 0.05 times a fifth, 0.10 times a fifth, 0.05 times. Okay, which one of them is 2/5? It's this one.
Should be 2/5.
There we are. Just in time to fix it. Times 2/5. Thank you for that nickel thing. And 0.01 times 1/5. And I think I screwed up because I don't like that answer. I did. I think I went and typed in some wrong there. So let's put everybody over 5.25 times 1. That guy, this guy, and this guy. And that adds up to 35, 45, 46. And I didn't screw up. It's just an ugly number. 0.46 divided by 5. The answer is 0.092. Which has to be rounded off. So I get 9 cents. In this particular combination, I get 9 cents, right? Your version might have different different numbers here, so you're going to get different. Does that one look okay? Is that what you were looking for, Tara?
Yeah,
Okay,
I think
you can
that I
hit the
got a
space bar,
little
I'll hear
better.
you
I
now.
was just getting confused and I was doing like on the 25 cents, I just kept it as 25. So I was coming up with these really weird numbers. I'm like, what am I missing? So you're just breaking down the fractions like for the probability. And then you break down if it's money, the decimal, but if it just gives you the amount, then you're just using that amount. And so like
because
when you're just figuring out and plugging it in. So that makes sense.
Yeah, when you did the spinner, the numbers were dollars, so it was still actually the same thing, right? Everything is kind of in dollar terms. Now, if you didn't do that, the answer you would get would be 9 cents rather than $0.09, which is 9 cents, but you know, it would be a different looking number. And the book was looking, I believe, the book was looking for dollars, so that's why 0.09. Are we good now with the expected values, spinners, all that good stuff? Okay, going to move on then. We are going to look at probabilities. We've seen quite a few of these. We're just essentially returning to them, adding a few extra things as well. This is our next section, 13.3. 13.3 is not due this Sunday. Right, your homework is up to the expected value this Sunday. The probability 13.3 that I'm doing and later on next week, 13.4, they're due the following Sunday, and your midterm will be up to and including those sections. So continuing with our topic, let's see what we have here. Before I talk about sample space, let's just remind you how to find the probability of an event. It is a number of ways event A could happen. And that's a whole number, and it goes on the top. And the bottom is the number of possible things that could happen. So just as a quick reminder, if I take a dice and I roll it, the probability that I get an even number when I roll a dice is 3 out of 6. And the reason it's 3 is that there are 3 even numbers on a dice. They're the numbers 2, 4, and 6. And there are 6 numbers on a dice. And so 3, 6 is the correct answer. But if it is a fraction that they want, you always simplify. If it's a decimal, you turn it into 0.5. If it's a percentage they want, you would convert it into percentage. So always be on a lookout for what version of the answer is. For instance, you could do the right answer and it's 3/4. And you type it in and it says you're wrong. And the reason it says you're wrong is it wanted the answer as a decimal or it wanted it as a percentage. So we've talked about that before, okay? We are going to look at now what are called sample spaces. A sample space is essentially the total, it's a list of all the different ways in which an event, or if you want to go an experiment, could happen. So sample space is a list of all things that could happen. I'm going to return to a particular sample space that I've used before. Let's look at 3 children families. They can be a boy or a girl, and we're going to look at how many, all the different combinations that you could get, and that's going to be our sample space. And it's always a good idea when you do these to have a systematic way of doing it. So I would do 3 boys. I would then do, the first 2 were boys and the last child was a girl. Or it might be you got a boy first, a girl in the middle, and then you finished with a boy. Or maybe your first child was a girl and the other 2 were boys. Or you could just have a boy and then have 2 girls. You could have a single boy, but he was in the middle. Or the last one that you wanted to get, the boy came last in your family of 3 children. And then the last possibility is that there are 3 girls. What we're going to make an assumption here is that of these 8 different things that could happen, that they're all equally likely. Now, it's not in reality exactly true. I think that the last figures I read, the probability that you have a boy is about 5:1, and the probability that you have a girl is 0.49. So it's close enough not to matter. But for theoretical purposes, we'll just assume that all of these are equally likely. So that if you are going to do probabilities involving things to do with 3 children, it's quite useful to have this first. So for instance, if I went and said to you then, what's the probability that you get 3 boys? Well, there's only one way to get 3 boys, but there are 8 possible things that could happen, and that's your answer as a fraction. If I went and said to you, what's the probability that your last child, right, out of the 3, was a girl? Then if you look through these 8, how many of these 8 was the last child a girl? Doesn't matter what the first and second child is, but the last child was a girl. How many of these 8 is that true for?
Four.
Okay, let's see it. 1, 2, 3, 4. Nailed it. In this case, you would do a half. Can you see you can answer all sorts of quite weird probabilities? Couldn't I say, what's the probability that the last 2 children were the same? That'd be a funny one, but I could do it. The probability that the last 2 children were the same, right? The same sex. Well, you just scan through the 8 and you say, okay, I know the bottom number is 8. Does that situation there, were the last 2 children the same? Yeah, they were both boys, so I'll count that one, right? Nope, they were different. They were different. They were different. That one counts, right? They were both girls, so that's 2. They were different. They were different. Last 2 were girls. That would be 3. Do you see in that question, the answer is 3/8. Now, if you did not have this sample space, and I went and said, in a family of 3 children, what's the probability that the last 2 children had the same sex? Do you agree it would be very difficult, if not impossible, to figure out the answer, right? So the benefit of a sample space is it shows you visually all the things that could happen. And then you just look at the question and you count how many out of the 8 are you talking about.
I have a question.
Yeah.
So maybe I'm just misunderstanding something, but I thought it was 4/8 because there's 4 of them, right? So there's a BB, there's a BB again, GG, and then a GG. So that's 4 out of 8, right?
Oh, are we talking about this last question?
Yeah.
Here? Okay, let me double check it in case I just screwed up. These 2 are boys, so I'm counting that as 1. Boy, remember it's the last 2 children.
Yeah.
So that means child 2 and child 3. So none of them, none of them, none of them. So that's good. That one counts, and that one counts. I can only see 3.
Oh.
Where did you think the 4th one is?
I thought on the second line that was a GBB.
I take it back.
Okay, I'm happy I'm not going crazy. Thank you.
No, I'm just careless. If you are careful, sample spaces are very useful. Of course, if you're careless, nothing is good. I would call with the sample space can help us answer quite weird probabilities because you'll have everything in front of you. It's just a matter of counting them, in my case, not correctly. But in general, if you count them right, you're going to be fine. So there's something coming in late.
Hey, really quick, I don't know if she's made it back, but I think Heather's trying to get back into the class.
Complementary, whoops, I'll just mute everybody. I'm sure they don't want us to hear their conversation. Complementary probabilities. And this something, it's a big name, but it's actually a very simple idea. Suppose you have the probability of some event A is 3/4. The complementary event has a little bar above it, right? And it's the probability that it's not A. So whatever happened is the exact opposite of A, the complement of A, right? And in this case then, can you see that it will be a 1/4? So the probability of not A is 1 take away the probability of A. And this guy here is called a complementary probability. Now you might say, why would I even want to know that? When could it be useful? It's quite specialized. You probably won't use it much, but there are some situations where you could use it. And sometimes you're doing it and not even realizing it. Oops, let me phrase that a little bit differently. What's the probability in a 3-children family that there were no boys? Well, one way would be, couldn't I count all the ones that had no boys in them? Right. Or couldn't I find the complement? What is the complement, or what's the equivalent of no boys? They're all girls. Great. And so when you did that, you might not have known it, but you were using a complementary probability. There are very few questions that it works for, so let me show you them. Suppose I tell you that the probability of A is a fifth. What's the probability of its complement? Remember, it's the rest, it's the opposite of it. 3/4 of the time this happens, 1/4 of the time it's not going to happen. That's what the complement is. It happens 1/5 of the time. What probability that it won't happen then? The other. No one to say a number.
4/5.
Yay, that's what I was wanting you to say. 3/17. What's the complement going to be? Do you notice that they add up to 1? Does that help? If this is 3/17, what's the complement going to be?
$14.
Yay. Let's do another one. What's the complement going to be? Nine-tenths complement. I'll take fingers.
1/10.
Yay. You were thinking I'm giving you a hard trick question there. I am not.
Yeah.
Have you noticed that the two of them always end up being 1? And there is good reason for that. The probability of an event plus the probability of its complement always adds up to 1. Because it's a bit like saying, what's the probability that it happens plus the probability it doesn't happen? Shouldn't that be everything? That should be 1. Well, that was a very short example of complementary. I think a couple of questions and that's it. So here's an example of it being used. You're going to choose a number between 1 and 100. What's the probability that you choose a number that's not a multiple of 5? Okay. If I think about picking a number at random, would you agree that there's 100 numbers from 1 to 100? If I said it's not a
20.
multiple of 5, we could figure out something a little bit easier. How many numbers between 1 and 100 are multiples of 5? Because it's easier to count them, isn't it, than the ones that are not multiples of 5, right?
20.
So there's well, yeah, let's check it. 5, 10, 15, 20, 25, 30, 35, 40. Blah, blah, blah. Can you trust us? She's right. There's 20 of them. So if I asked you what's the probability that it is a multiple of 5, your answer would be 20 out of 100. But I want to find the probability that it's not a multiple of 5. Don't you just look at complements? Because these are complements. And the answer, 80 out of 100. So that's me using complements. Sometimes it's easier to find the opposite of what you're looking for than it is to find what you are looking for. It's easier to find all the ones that you can do multiples of 5 than it is to write down all the ones that are not multiples of 5, right? You could do it, But if you did, wouldn't you end up with 80 numbers? I'm saying it's just quicker to find the opposite event and add it up. And that's kind of the gist of what's going on here. So I put a little boundary on complements. Next fella. Wow. This is question 5. And in question 5, they have 4 children family. Now, I'm definitely not going to do this question in total, but I think you probably need to start to it. You want the sample space for this. When it's quite big and awkward, wouldn't it be helpful if we knew how many things there were in the sample space so I could know when to stop looking? Right? So, there are 4 children. We are going to use a technique called the counting method. And it's quite useful for finding out the total number of things in a sample space. So this is going to be the first child, the second child, the third child, and lastly the 4th child. And the way the counting method works is that if you do something like 4 children family, you write down how many things can happen in each of the 4 situations, and then you just multiply them together. So for instance, isn't there 2 children, a boy or a girl, that could be your first child? And wouldn't your second child could be a boy or a girl? Your third child could be a boy or a girl, or your 4th child could be a boy or a girl. So what you end up with is 2 times 2 times 2 times 2, 2, 4, 8, 16. That means there are 16 things in the sample space, right? 16 different things. And then you have to have a systematic way of writing them down, right? It's not a good idea to just randomly say, oh, boy, boy, girl, girl, 3 boys, a girl, 2 boys, a girl, and just randomly pick them. It works well at the start. Won't you probably get about 10, 11, 12 of them pretty quickly? But when you do that method, isn't it really hard to get the last couple? Because they're just all over the place. So here is my suggestion for children family stories, but you can do it for other things as well. Just start with an extreme. Start with 4 boys. And then the next column, 3 boys and a girl. And I'm going to go 3 boys and a girl at the end. Then 3 boys with the girl in that position. 3 boys with the girl in that position. And then 3 boys with the girl in that position. Do you see how I'm systematically doing 3 boys with 1 girl? And it's easier if you keep it in a kind of pattern. What's going to be my next chunk of people? How do you think I'm going to look at it next? This is 3 boys and a girl that I've just done. So what should I probably do next?
All girls.
Oh, well, that would be
Or
a way over there.
you could do
And I
2
would,
boys, 2 girls.
yeah, I want to kind of keep the pattern going. So 2 boys and 2 girls is a little bit harder to do systematically. So I want to make sure that I write down every single possible way you can get 2 boys and 2 girls. So I'm going to go this way. I'm going to go 2 boys. Now what I've done here is all the ways you can have 2 boys and 2 girls, and I've kept the girl at the end. You see, the girl, she's still there. And I just moved her. Now I'm going to go back, and now I'm going to do the 2 girls in the middle. And then I'm going to do the girl at the end. And then I'm going to finish with the 2 girls and the 2 boys. And so the way my brain has worked, I think I've got every single combination of 2 girls and a boy. Can you think of any combination that's not already written down? That's a good sign that you've done it right. Now, the next one is going to be easier because it's simply just going to be what? 1 boy with 3 girls. So 1 boy with 3 girls, 1 boy, 3 girls, 1 boy with 3 girls, and 1 boy at the end. And lastly, the one you wanted, all the girls. Now, if I've done this correctly, shouldn't there be 16? Agreed? If this is all the sample space, there should be 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I found them all. Right, there are 16 there. I know I'm good. Now, you may find a different systematic way to get all 16. And as long as you get them all, it really doesn't matter. Did anyone have a different strategy for getting these 16? Be interesting to hear if you did. Don't hear any other versions, so this is as good as any. Right, now, the rest of the questions are the same kind of questions we've done before, so I'm not getting into this. What's the probability you get 1 boy and 2 girls or 3 girls? What's the probability that the last one's a boy? What's the probability that they're all 4 boys? In all of those questions, aren't you just going to have 16 in the bottom and then you just count through these, whatever it is? So if I said, what's the probability you get 2 boys and 2 girls? Right, suppose that was the question. What is the probability that you get 2 boys and 2 girls, right? In any order that you want. It would be 1, 2, 3, 4, 5, 6. Be 3/8. Let's try one just to finish this. Let's try a weird one. What's the probability that your last 2 children are both boys? So I'm scanning through, and I'll try not to screw up this time. The last 2 children are both boys. That one, that one, that one, that one. Hopefully I didn't do anything wrong this time. There's a 1 in 4 chance that in a 4 children family, the last 2 children were boys. That's what we've just discovered here. Does anybody come from a 4 children family?
I do, and they were all girls. I was just thinking, wow, that was really unlikely.
It is, isn't it? Because according to this, isn't all girls 1/16? Now, it's not impossible, right? 1/16 just means if you collected 16 random families with 4 children in them, one of them would have been your family, right? The one with the 4 girls in it. On
Yeah,
average,
poor father.
right? You're darn tootin'. Well, will you want to give some sympathy for me? Have I told you I come from a family of 10, right? Did I tell you that I also came from a family where bad luck happened? Because my mum and dad had a boy first, and then they had 6 girls before they got me. So if you think you're poor dad, do you want to give me a little bit of a break here? Can you imagine being
Yeah,
brought up
that's a
with so
lot
many
of
female?
girls.
That's a lot of girls to be in front of you. Yes. My wife, yeah, Celeste has said to me that it has changed certain parts of my personality. It's not that I'm very feminine, because I'm not really, but there are certain things I do that she thinks has been caused by that. I don't swear a lot. And she thinks it's because when I was younger, having all, it's sexist that girls don't swear, but, in my family, they didn't anyway, right? So that's where that came from. My dad swore like a trooper, and my mum never swore at all. So there was a definite disparity in behaviour. My dad thought it was hilarious to learn the kids. Give you a quick story here. My mum was basically a mother all her life. When my mum was 12 years old, her mother died in childbirth, which was quite common the way back. We're talking close to 100 years ago now. And so what would happen in those days, and because it wasn't that uncommon, was that if there was an old enough girl in the family, that she just left school and she looked after the new baby. So my mum became a mother at 12. She looked after her own sister, little baby sister, fed her, did everything since she was 12. And then later on in her life, she married my dad. And she married my dad quite young. She was 18. So that was like 6 years, just enough for her own little baby that wasn't hers, genetically at least, to be old enough to look after her. So she got married and she started the family. And then once the family got old enough, my mum was having her last baby when my brother Billy was having his first. So what my mum ended up doing then was looking after the grandchildren while their mothers or fathers went to work. It was mostly their mothers, because all of my sisters. So children everywhere in our family. So the story I'm finally getting to is to give you an example of how hard my life was with all these. I had essentially 7 mothers. I had my mum, and I had all my big sisters. And all my big sisters had one job, it seemed to me, and was to be my boss, to make sure that I didn't do things, and to tell on me when I swore, and who knows what else. And when I was very young, they took me out and they put bows in my hair, because I had long hair, put bows in them and ringlets, and put fluffy baby dresses on me, because I was a little, 1-year-old baby. Really did some cruel things to me like that. And anyway, what happened in this story was that they were pushing me around in the pram. And one of the neighbours looked at the new baby and said, "Oh, it's a cute baby." And on the next day, he met my dad, and he said to my dad, I saw your new baby. It's a beautiful little girl you've got there." And my dad said, "Not a girl, that was my boy." And well, my dad, when he figured that, it wasn't happy. And so essentially from being 1 year old, my hair never got longer than about 1/4 of an inch. It was called a crew cut. I guess it's a sailor's cut in America. Do you know the ones where you can basically see your head through it? That's what my hair was like. And I never knew what long hair was until I went to university, and I did that rebellion thing where you grow your hair long. And I grew my hair long, and I did it for about a year. And then long hair is a pain in the butt. You got to wash it, you got to dry it, you got to look after it. So after 1 year, I just said, to heck with it, I don't like long hair, and I went back to short hair on my own volition. So there was a little memory from the past. So it's not nice that you do things like that to your little brothers and sisters, so be kind to them. Right. Aubrey, do you have a little brother or sister?
Me?
Yes.
Did you say Aubrey? I'm actually
Yes.
the only girl. I have 2 older brothers, me, and 1 little brother. I'm the only girl.
So what's it
of
like
four.
being in a house with all those boys then? Do you feel the same kind of pressure that I got, but in a different way?
Kinda, because all boys, they're dirty, so I had to do all the cleaning. Especially when you're in an Asian household, your mom expects you to be very ladylike. But I wasn't, because I was around all brothers, so.
You ended up being a kind of tomboy because of their influence.
Yeah.
I hear
That's
you.
what everyone says. Like, since I'm very competitive, I got that from my brothers. How about, like, I'm independent, I got that from them. So same
Oh,
way.
so you got some positives from you.
Of course.
Right. Well, we are about now to do a probability question that seems impossible, but it's not. You may or may not have heard of this family, but they're called the Emery family. They're from Tennessee. And this family had 13 children, and every single one of them was boys. So you thought you were unusual with 4 girls. We are going to find the probability of getting 13 boys. Now, before you freak out, we are not going to do a sample space of every possible 13-child family. Can you trust me? If I did that, I don't have enough paper on the table here to write them down. So there must be another way of calculating the probability that all 13 are boys. Now, all probabilities are 2 numbers. The top number is easy. If there's 13 children and they're all boys, isn't there only one way that can happen, right? Boy, 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 right? We got that one. All I need to know is what the total number is at the bottom. And can't we use the counting method? Right. Now, the counting method says, okay, first child times second child times third child times blah, 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 times 13th child, right? And isn't that going to be 2 boy or a girl times 2 boy or a girl times 2 boy or a girl? And I could write them all down, but isn't that the number 2 being multiplied 13 times? And in math, isn't 2 to the power of 13 the short way of saying 2 times 2 times 2 is 13? Which means I can now go and get the calculator to tell me what do you get if you multiply 2 times 2 13 times. And the answer is 8,192. So the probability that in a 13-child family, all of them are boys is that, as a decimal, because that's what they wanted in this question, it's this weird number. I don't know if you've ever done any calculations, and a weird E thing has appeared like it has here. Do you know what the calculator is telling you? Do you know what that means when you see a decimal and an e to the -4 or the e to a 7? You might have seen it in chemistry, perhaps. You might have to hit the space bars because I kind of muted you out for background sound. So if you want to say something, you'll have to hit the space bar.
I was gonna say, sounds like you need to change your mode from scientific to non-scientific, or it's just.
Oh, you just want to avoid the thing, right? Well, I guess so. What it means you're right, it's scientific notation. It means that. It's not too difficult to convert it because all I think of is e to the -4 is essentially 4 zeros. So that is the answer as a tiny little, almost impossible number. But evidently it's happened once, but it happened so rare that it ended up in the newspaper. You'd like to see that family, wouldn't you? Let's show you them. There they are. Would you look at that family?
Talk
And there's a
about
little baby.
having
6 girls, 13 boys. Seriously, I feel bad for that mom for so many reasons.
Yeah, it's hard to think of a, well, the problem with having 13 children is which ones do you want to, which ones do you want to give away? I mean, once you've got them, you got to keep them, right? But yeah, can you imagine just simple things like making a meal?
Or having to clean up
God, it
after
could ruin it.
everyone.
Yeah, not good. Not good at all.
But
it's very
then
rare
again, she may actually like it.
to
So
have that. My mum, with all the children she got, loved being a mother. Just, she loved children. She just loved any child. You know, if my mum was walking down the street and there was a baby crying, she had to, you know, control herself, because she would have picked the baby up and, you know, patted it on the back and, you know, try and make it feel better. And a lot of parents do not like strangers for very good reasons doing that. So she would have done it if you let her. She would have. She loved children. Got stories in my head. You've done this again. I'm blaming you this time, not me. Told you about my dad would swear like a trooper. He thought it was fun that when the grandchildren came in, my mum was looking after them. He thought it was fun to learn them swear words. And one of my sisters had a little girl, Amy, and he learned her, you know, a full swear word. And the minute her mum came in from work to get picked up, the little girl went over and, you know, hi, actually about 3 or something. Hiya, mummy. And she said, how are you? And she said, oh, I'm good. And beep you. And she went, oh, God, what? No. Right? And so she didn't panic. She went and said, who learnt you that? And she said, Grandpa. And she said, oh, God, that's it. Exactly that. And you know, once they learn that word and they're that age, it's very hard to unlearn it, because don't they want to use it in every, you know, people would come into the house and she would go up and she'd go, beep, you know, beep you, beep this. And she loved the reaction, you know. It was great fun. And and I figured out what I thought was a plan to stop it happening. So I was talking to my sister Mary and was saying, look, what we're going to do is I'm going to pretend to get angry, and I'm going to use a totally safe word. And the word that I ended up deciding on was called MFI. And the thing about the word that's actually 3 letters is that you can actually put a lot of vehemence in it. So I would go MFI like that. And we knew what was going to happen. So she was sitting down playing with her doll, and Mary was there, and there was something on the TV, and I pretended to get really annoyed. And I went, oh, MFI. And Mary done the whole, God, Donald, where'd you learn that word? Right, went over the top, never use that, you know, the whole thing. And her little ears, you could tell her little ears were waggling. Forget the beep, this is better, MFI. And she didn't use it right away because, you know, I guess she was thinking about it. And a day or 2 went by, and she was playing with her doll, and she got annoyed with her doll, and she threw it on the ground, and she went, MFI, you know. And we were ready for it. We done the whole, who did you learn that word from? And that's terrible, and never use that word again. And it was working great. Forget about beep. She wasn't using that word anymore. It was MFI. And people would come into the house now, and she'd go up to them and go, MFI, you know, and MFI. Great. And do you know the only problem is that kids are clever. And you can con them for a little while, but you can't con them forever. And the problem with MFI was that the reason I picked it was it's the name of a company like, do you know the flat pack companies where you buy furniture and you build it yourself? They're called MFI. That was the name of the company. And on television, there was an advert that came up, and sure enough, the advert for MFI came up, and the guy on the TV was saying, you know, turn up tomorrow for the sale at MFI. And, you know, he'd say it 4 or 5 times, and you could see that she figured it out. And that was the end of MFI. But if you ever have a child that is swearing, it might be worth trying. I think you can get it away with it for a 3-year-old. By the time they get to 4 or 5, forget it. They are too wise. It'll just not work, right? So, see the things you learn in this class that are nothing to do with math. Tara, have you had problems with swearing children yet?
Yes, my youngest father allowed her unadulterated access to YouTube. And I came in, she was 2, and she was beating the crap out of her brother, calling him a mother bleeping B word.
A beep beeps, the beep beeps. Yeah.
Oh, yes. Telling him to give her the candy. He hid his Halloween candy.
Oh, God.
Because she saw it on one of the videos where this lady was yelling at somebody, calling them that and beating them up. So yeah, needless to say, I didn't know what YouTube was then. I do now.
Okay, now you know. Well, the joys of parenting. So you don't think MFI might work?
No, she already
let's-
knows. And she's 6 and she kept it. So when she gets really mad or she wants a reaction from someone, she'll just say it. Because she knows every single adult reacts like they're like, oh my gosh, where did you hear that from? Yeah.
Yeah. I hear you. Okay, next topic and probability is going
Can you
is
tell
called
me how you
conditional.
figured out the one? Can you tell me how you figured out the one part? Because I've been puzzling it through. I got the 1892 on the last question, but I couldn't figure out how you got the decimal point from there.
This to here? Is that what you're saying?
Yes.
Right.
So
when
where did the 122 come from?
Okay. When you take this guy here, did you get the scientific notation, which is what the calculator says?
Yes, I
Right.
got that. I got to the 8192, but then I got lost.
Okay, so you take 1 divided by 8192, and the calculator will come back with an answer that looks something like this. It has other digits, but these are the only ones I've written. So if I put this into the, so if I go 1 divided by 8192, and you can see the 2 there. The rest I'm ignoring because you don't need it for the accuracy. And then what I had to realize is that this is the equivalent to the scientific notation, which is that. And if you're in chemistry, that would probably be a valid way of writing the answer, but we don't like that. So what I'm saying is that if you want to take a -4, add 4 zeros to the front, and then just write the 3 digits down. And this is what the decimal version of that looks like. So these are equivalent, and that's what they look like. Are we good so far? Right. Next fella is conditional probability. Now I'm just going to do the pause thing again. The mute thing, I guess. There we go. So what we're going to look at here are probabilities where you know an extra piece of information, very often called the condition. And they're written using this notation, a vertical line. And you read this out loud as the probability of event A given that event B has happened. So you know that something has happened, that event B has happened, and that's the condition. This funny little symbol is basically the word given. So the probability that A happens given B would be the shortest way of saying that. So the probability of A given that B has happened. There are a number of different situations where we're going to be doing with these. The first one we're going to do is questions involving cards. They're quite common for these types of questions. I think I need to write down a little bit about cards because not everyone is familiar with them. We're talking about a normal deck of cards, no jokers or anything weird, right? Just normal cards. And in cards, there are 4 suits: clubs, diamonds, hearts, and spades. And the clubs are red and the hearts are red. And the diamonds are black in color. Nobody even caught me. The diamonds are red and the hearts are red. The clubs are black and the spades are black. And each of these are called suits. Each of these suits have the same cards. They have an ace, and then you go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then you have 3 other cards called jack, queens, and kings. These 3 cards are called face cards. If you ever see a picture of them, I think they get the name because they're people's faces and you can see a face in them, right? The jack, the queen, and the king. And this A up here is called an ace. And each of the 4 suits have the same combination. So there's an ace of clubs, an ace of diamonds, an ace of hearts, and an ace of spades. So the kind of conditional probabilities that we're going to deal with are the probability of, say, picking 1 card, right? And you're given an extra piece of information. So let's show you how that might work. What's the probability that you pick a card from a deck of cards and it's a king? Well, there are 52 cards in a deck and there's 1 king from each of these 4 suits. So the answer is 4 out of 15, which is simplified down to 113. That is a normal probability. 4 kings, 52 cards, cool. But you might get, what's the probability that you get a king given that it was a face card? So someone tells you, right, you know something, you know that it's a face card. Now, how does that change the world? Well, on the bottom, it's going to be the number of face cards. Now, a face card is jack, queen, king. So there's 3 clubs, there are 3 diamond face cards, 3 heart face cards, and 3 spade face cards. And that's going to come to a totally 12 face cards. Now, of those 12 face cards, how many of those 12 are kings? Well, there's a king of diamonds, a king of clubs, a king of hearts, a king of spades. There is 4. And that simplifies down to 1/3. So do you see that those 2 probabilities are different now? If you just randomly pick a card from a deck, there's a 1 in 13 chance it's a king. But if someone tells you it's a face card, right, you know that is true. Do you see the probability is now improved, right? It's more likely to be a king now that you know it's a face card, doesn't it? Than before when you knew nothing about the card. And conditional probabilities tend to do that. And sometimes they can affect things and sometimes they don't. And you might think, what do you get? Well, here's another king question. What's the probability that you get a king given that it was a red card? Okay, red cards go in the bottom. There are 13 red diamonds and there are 13 red hearts, so that's 26 cards. Of those 26 red cards, how many of those are kings? Someone could answer that one. How many of those are kings?
Would that be two, one in each?
Yeah, one, what would that be? One diamond and one heart. And that simplifies down to 113. Oh, do you see in this case, the conditional probability had no effect? The answer ends up being the same. And you could say, well, why is that? Well, do you know the chances that you get a king when it's a red card are the same chances you would get a king if it was a full deck? Right, there's not a lot of give there. Here's a weirder one. What's the probability that you get a king given that it was a 10? So somebody says, I know the card was a 10. Well, the bottom goes 4. How many kings are there when the cards were 10s? There are none. Do you see, in that case, you get the silly answer, or maybe not silly, but you get the answer that the probability that you can get a king, given that it was a 10, is a big fat 0. And then you think, well, of course it wouldn't harm, right? If it's a 10, it couldn't be a king, right? Are we cool with it? I'm seeing puzzled faces with that last one. Does that look okay to you? Let's move, try another one then, if that is okay. What's the probability that you get a club given that it was a black card? Okay. How many black cards are there in a deck of cards? So how many black cards are there in a deck of cards?
26.
Agreed. Of those 26 black cards, which are the spades and the clubs, how many of those are clubs?
13.
And so this probability is a half. Do you see how the conditional probabilities move around depending on the condition? What's the probability, a non-conditional one, just a straightforward one, of getting a club? Well, there are 52 cards in a deck where nothing else is known. 13 of them are a club. Do you see that your odds have got better when you know it's a black card? Well, here's another one. What's the probability that you get a club given it was a red card? Well, there are 26 red cards. How many of those are clubs? It's almost a silly question.
None of them.
And so the chances of that happening are 0. See, that's another one of these weird 0 things. Do you see they can happen? So don't be distracted by the fact that you could get 0. Here's another weird one. What's the probability that you get a face card given that it was a king? Well, I know there's 4 kings in a deck, right? So the bottom number is 4. How many of those 4 kings are face cards?
All of them.
Right. So isn't that a guaranteed probability of 1? So conditional probabilities could be 0. It ain't going to happen. Right? The probability you get a club when it's a red card would fall into that category, right? This one up here. And couldn't the probability be guaranteed? Like, what's the chances that it's a face card given it's a king? Well, a king is a face card, so it's guaranteed it's going to happen. Can't you sometimes improve your probabilities? Right? They get bigger. Sometimes you can make them smaller. The information you get, the condition that you get, will change the outcome to a probability. Here's one I'm looking at right now. It's a version question 8. What's the probability that you get a club given that it's not a heart? Okay. If you're not a heart, that means you're those guys, right? And would you agree there's 39 of them, right? If you're not a heart, you're those guys. So 39 on the bottom. Of those 39 cards, how many of them are clubs? How many of these 39 cards are clubs?
A third of them.
Yeah, 39 to 39. A third of.
Professor, I have a quick question. Over in your
Yes.
diagram about cards, don't decks of cards
Mhm.
have number values that start at 2 and go through 10, or do they have number 1 as well?
Oh, here, my apologies. The A is a 1 sometimes. Depends on the game you play. An ace can also be worth 11 if you play blackjack. But you're right, it should only be 2 to 10. I just made a mistake. So you caught a mistake. That was good. Right, this is going to be the last card one with a single one. This is a version of question 9. And I don't know why they seem to like jacks, at least the one I've got. What's the probability that you get a jack given that it was a black card? Well, there are 26 black cards. Great. The black cards are clubs and spades, 26 of them. And of those, aren't 2 of them jacks. So your answer would be 130. So far, so good. We have just done card questions where you take one card from a deck and you find some type of conditional probability using one card from a deck. We are still on cards. We're going to up the ante and look at 2 card questions. Now this gets a little bit harder. In this story, it's the same story each time, so I'll just write it down once, but it's in all of them. 2 cards are drawn from a deck. The first card is noted. In other words, you look at it, you write it down. The first card, right? You find out what it is. It's then thrown away. You then take the second card from the deck. And we are going to look at probabilities of what that second card is going to be like. So here's an example of what that would look like. What's the probability that the second card is a heart, given that the one that they threw away, the first card, was a heart? Now, in these questions, the probabilities are going to be calculated a little bit differently. It's still a conditional probability, but we have to take into account the information. There's only one card that we know about. The first card is a heart, right? That's given, right? That happened. And that one heart was thrown away. So doesn't that mean that the bottom number is 51 now? So in these stories, the bottom number is 51. Remember in the other stories, if it was a black card, it was 26. If it was something else, it was 4 or 8. You see how that bottom number kind of changed depending on this. That was the 1 card situation. In the 2 card situation, can you see that it's a single card? You know what it is. You take account of it. So now we need to figure out who the top number is. There normally is 13 hearts in a deck, agreed? But in this story, wasn't the first card a heart? So didn't that get used up? Can you see that the answer is now 12 out of 51? Are we good with that? Are you happy with how that condition worked? So you take the first card that's a heart. Oh, it's a heart. Okay. Cool. What's the chance that the next one's a heart? The answer is 12 out of 51. And here's a little thing that I didn't even notice till I looked at the answer. You type that into WebAssign and it'll say wrong. And it's not I made a mistake. Can you see anything? Because I didn't notice until I looked. Do you see anything about this fraction?
4/17.
Yeah. I don't know about you. I never saw it. I never saw that that one could simplify. I mean, it's well hidden, isn't it? It doesn't look like numbers that should go into each other, but they do. 3 in the top, 3 in the bottom. So that's what you needed to do. So I could imagine if you were doing your homework and you didn't notice that, you'd get really frustrated by why is it not right? Well, it was kind of right, isn't it? But you didn't round it off. What's the probability then? Same story, right? I won't be putting second card and first card in now. What's the probability that you get a king given that, what shall I do? Given the first card, given that this card was a king. Ooh. So the first card is a king. That means you've got 51. How many kings are left now in this story?
Would it be 3?
Yeah, because the first one's a king and it get threw away, and there's only 3 left. And by the way, that simplifies as 117, so I'm getting used to this now. Try another one of these. What's the probability that you get a heart on the second card, given that it was a black card that came out the deck? Right, so 51 goes there. These questions are always going to be 51 in the bottom, right? Because it's one card, you look at it, it'll happen to be a black one, you threw it away. What's the chances you get a heart? Here's the top number.
Would it be 13? Because heart cards aren't black, they're red, so it wouldn't be changed.
And it won't be changed. Yep. I don't think that one simplifies, so that's your final answer. Do you need any more of these, or you feel comfortable with them? Do you want another couple of examples of a 2-card deal where we look at the first one, we throw it away, and then we do another? Okay. How about, what's the probability that you get a club given that the first card was the ace of clubs? Right, there's still 51. Who's your top number? How many clubs are left? Because that's your
Maybe
top
12.
number. Yeah, because didn't you use up the ace of clubs? If I had said to you, what's the probability that the second card was a club, given that the first card was also a club, wouldn't you still get 12 out of 51? Oh, by the way, which that one simplifies down. Because it doesn't really matter which club it is, isn't it just going to be the same probability that the second card is a club. Knowing it's ace of clubs isn't actually that important. Being a club would be important. I'm running short of examples of this, so there are only so many I could think of. What's the probability that you get a 2 given that the first card was a 2? I'm kind of repeating myself with these questions now. How many 2s are left in this story?
3.
3.
Just 3, which becomes 1/17. I'm out of questions. Every question I could think of. There are only so many ways you can do these questions. Oh, how about this one? Okay, what's the probability that the second cards are red, given that the first one was a black card? So if the first card is black and you threw it away, how many red are still left?
Wouldn't it be 26?
Yeah. I think you can simplify that one, so there's your answer. If I, just out of curiosity, suppose I come across a fraction and I'm thinking maybe it simplifies, maybe it does, and maybe it doesn't, and I don't know. You could go something like this: 26 divided by 51, get the ugly guy, hit the math button and convert it to a fraction. Do you see it just goes back to where it started? That means you can't do anything to it. On the other hand, if I did something like 12 over 51, there's the decimal, math button, choice number 1. See that one goes 4/17. So, I mean, the calculator will simplify fractions for me if I forget to, or I don't notice that it could be done. So that is conditional probabilities with cards. And the last one is using dice. So we're going to do 1 dice first and then 2 dice. And that's kind of all we need to worry about. What's this time? How long have I got? Tons of time. Great.
Can I ask a question?
Sure.
So I know this is for the homework that's due pretty far in the distance, right?
It's a week on Sunday.
Yeah. Are we going to have any like review on what the exam's going to cover, or do we just need to use our homework to review?
You should start doing the homework just right now, but next Thursday, I'm devoting all of next Thursday to review for the midterm.
Oh, okay, thank you.
Right, because what's going to happen is the midterm, oh God, it's hard to keep track of the days, but we still have a whole week next week to do, and then it's the following Tuesday that the test will happen. So what would that be? A week on Tuesday is the midterm exam. Maybe that's the easiest way to say it, right? So what, about 12 days away? Still a fair amount of time. Right, let's do a 1 dice story. Draw a little picture of a dice because I can. 1, 2, 3. You know a dice has got 6 numbers in it. They're very easy, single probabilities. Let's do an unconditional one just to get the ball rolling. What's the probability that you roll a dice and you get an even number? There are 6 numbers on a dice, 3 of which are even. The answer is a half. Can't really do much more than that. Let's do conditional probability then. What's the probability that you get an even, that you get a 6, given that it was an even dice? Now, the fact that you're told that it was an even number, doesn't that make it 3 numbers? I mean, if I write down all the numbers that can happen on a dice, if I tell you it's even, aren't I basically telling you it's one of those 3 numbers? So that's where the 3 came from, right? How many ways can you get an even? Would you agree that there's only one way to get a 6? So the probability of getting a 6, given that it's even, is 1/3. Right? There's only one way of getting a 6 out of 3 even choices. Now I'm going to switch this guy around. What's the probability that you can even number when you throw a dice, given that it was a 6? Well, there's only one number 6 in the dice. Would you, I'm not even sure I need the calculation for that. Would you agree that the answer there is 1? Now, let's see what that means. What's the probability that it's an even number, given that it's a 6? Isn't it guaranteed to be even? Right? It's a 6, right? It's even. This way round's a little bit different, isn't it? It could be the other one. It could be a 2 or a 4. So that's why it's not a guarantee. What's the probability then that you get an odd number on a dice, given that it was even? And I'm not even going to do this guy as a calculation. What's the probability that you roll a dice and it's an odd, exactly, it's an odd number, given that it was an even number? 0. So can you see that with dice, there's less questions that you can ask with a 1 dice question, because there's only a very, very limited number of things that can happen. You might get 1, you might get 0, or you might get some alteration. And because an unaltered version isn't the probability of just getting a 6, 1/6, but the probability of getting a 6 when you're told that it's even, doesn't it improve? Because it's easier to get a 6 when you know it's an even number than it is to get a 6 if you don't know anything. Are we good with the 1 dice, guys? Because there's not too many questions you can really ask with those. Now the one that does require a lot of work. You know, if I had a brain, I would have planned this out, which of course I didn't. So you or lot are going to have to wait while I create one of these darn things. Although you might want to make one your own while we're at it. Okay, let's assume that we have 2 dice and we'll color code them. My first dice is red and my second dice is green. And the reason I want to distinguish them is to make sure that we're clear about the order that the dice get rolled is just as important as the numbers. So first dice, second dice, and yeah, I'll do it in black. I apologize for this. I should have printed some or whatever. And I cannot multitask or I'd be telling you a joke right now. There we go. This table is basically the sample space for the 36 things that can happen when you roll 2 dice. And I know that there's 36, but I'll show you how I could find out. First dice times second dice. 6 numbers on the first dice, 6 numbers on the second, 36 things that can happen. And there they all are. And you look at these dice, these things that look like coordinates are just a way of writing it down. For instance, this one here would represent a 3 and a 4, right? The red dice was a 3 and the green dice was a 4. This would be a double 6. This would be a 6 and a 2. This would be a 1 and a 4. I think everybody's probably familiar with dice. You use them in lots of board games, so I won't need to go hopefully in too much detail with that. Now we're going to look at probabilities involving 2 dice. And there are a number of different versions of questions that use these. You get ones involving total. So what's the probability that you roll 2 dice and the total is 10? So in this case, there are 36 different things on the bottom. And then you go through these and you find out all the ways in which you can get a 10. 6 and a 4, a double 5, a 4 and a 6. There are 3 ways to get a total of 10. That simplifies down into the probability of 1/12. Are we comfortable with the total kind of question? What's the probability you get a total of this or that? For instance, what's the probability that you get a total of the 2 dice and they add up to 3? Well, if I look at my list here, 2 and 1 adds up to 3 and 1 and 2 add up to 3. So that's going to happen 2 times. And that is 1/18. You can, of course, have things like this. What's the probability that you get a double? Hopefully you're familiar. A double means both numbers are the same, right? You get a double 2 or a double 6. In this case, 1, 2, 3, a double 4, a double 5, and a double 6. There are 6 ways that can happen. So far, so good. As long as you've got this, can't you figure out by counting the top? It depends what you're being asked to do. How about something a little bit different? How about the probability that the green dice is a 6? Right, now you look at this one. The green dice is a 6. Well, it might not look very green. It looks blue now in my screen, but it is green. Is these guys here, right? And that only happens 6 times. You can also do things like this. What's probability? At least 1 dice is a 6. Okay, I'll let you count that one for a few moments. Out of the 36 dice combinations that are here, pairs of dice combinations, how many of them has at least one of the dice as a 6?
$11.
Well done. Yep, 11. There we go. So okay, I can simplify that one. So are you comfortable with how this table can help you answer these types of questions? Do you need to see more of these ones? Or you do? No. So we're cool. The bottom number's 36 and the top number's just, count whatever it is. I mean, I could do all sorts of things. Can I say what's the probability that the total is 10 or more, right? Maybe I should do that as my last one then. What's the probability that the total is 10 or more. Well, the bottom number is 36, and I just go over and say, okay, then 10 or more, that's a totally 10, which is those three, and then a total of 11, which is those two, and then a totally 12, which is that one. So 1, 2, 3, 4, 5, 6, and I get 6 out of 36, and the answer would be 1/6. So as long as I can count which ones work and stick it over 36, we're good. So the last type of question is conditional probabilities. So here's an example of one. What's the probability that you get a total of 10 given I'm trying to think of how to phrase this, a green dice, yeah, a green one is a 6. Oh. Now, if you're told that the green dice was a 6, what's the probability that you can get a total of 10? Well, the world has now changed. If you look at this table, how many of this table have a green dice of 6? And the answer is it's only the bottom row. There's only 6 of them. And of these 6, how many of them add up to 10? I can only count 1. So the probability that you got a total of 10, given that the green dice was a 6, is only going to happen 1 out of 6, right? That's the chances of it happening. What's the probability that the dice, right, the die has a 4 in it, given that the total was 6? That's going to be a hard one to count. You're told that the total was 6, and what's the probability that the dice has got a 4 in it? So when I look at total of 6, I'm talking about that guy, that guy, that guy, that guy, and that guy. So that's 1, 2, 3, 4, 5. There are only 5 ways in which you can get a total of 6. And I'm actually going to write them down. It's a 5-1. You can get a 4-2. You can get a 3-3. You can get a 2-4. Or you can get a 1-5. Right? That's the 5 different ways in which a total of 6 could happen. Of these 5 different guys, how many of them have a 4 in them? That's 1. And so is that another one. So in this case, the answer would be 2/5. So do you see conditional probabilities don't just change the bottom number, don't they also change the top number? Because there's a lot more ways to get 4 if you didn't do that condition. I'm going to give you one really horrible one to try for the finish for today. What's the probability? Let me find one that they've got. What's the probability that you have a 6? Right? So one of your dice is a 6, given that the total was greater than 9. So I don't know if I can make this bigger for you. There. That might help you if you're using my answers. What's the probability that one of your dice is a 6? Right. And I'm going to phrase that a little bit more precisely. Exactly one of your dice is a 6, given that the total was greater than 9. And I'm giving you 2 minutes. Go for it. Be careful. There's a trap in this question. Okay, here goes. Let's do how many ways this can happen. For the total to be greater than 9, doesn't that mean the total's 10, 11, or 12? So if I look at 10, it's these 3 guys. 11 is these 2 guys, and 12 is this guy. So there's 1, 2, 3, 4, 5, 6. So you're talking about 6 things here. You're talking about a total of 10, 11, or 12. So the world really consists of, can I do it with a pen maybe? It really consists of just these 6 guys here, right? And I phrased it very precisely. Exactly one of the dice is a 6. So how many is that?
That's you only get a total of 5 different combinations because the one with the one that adds up to 12 wouldn't be part of both of them.
Correct. You're breaking up. I think I caught the gist of what you were saying. And so you were saying that that double 6 doesn't count.
Right.
So the only ones that you use is this one, and this one, this one, and this one. So your answer would be 4 and 2/3. So 4, 6, and it simplifies as 2/3. Do you get the gist that the double 6 was the non-usable one? And that's why I was very precise about that.